Hi, I'm Michael and I'd like to show you how you can use the Chinese remainder theorem to solve systems of congruences. Just to make sure we are on the same terms here, a congruence is something that looks like this. X is congruent with y modulo m. And what this means is that there exists some k, which is a whole number, such that m times k plus y is equal to x. Well, the choice of x or y doesn't matter here. You could also write it as there exists an k in the set of whole numbers such that m times k plus x equals y. What this means is that x and y have the same remainder modulo m. For example, 15 is congruent with 0 modulo 5 because 15 is equal to 3 times 5 plus 0. 0 is the y, 3 is the k. Or also 14 is congruent with 19 modulo 5 because 19 is equal to 5 plus 14. Or also because 14 modulo 5 is equal to 4. The operator of modulo denotes the remainder after whole division, and also 19 modulo 5 is equal to 4. When those two equations are true, then you can write it as 14 is congruent with 19 modulo 5. Okay, so that should be enough for refreshing what congruences are. So, a set of congruences like x is congruent with 5 modulo 7 and x is congruent with 4 modulo 9 and x is congruent with, I don't know, 2 modulo 5 is pretty much the usual sort of problem you would use Chinese remainder theorem to solve. Chinese remainder theorem can be applied if those numbers are all relatively coprime. That means that when I take any of those numbers, like 7 and 9, then their greatest common divisor is equal to 1. Okay, the basic principle behind the Chinese remainder theorem is that you can find some, I will denote that by p, some number p1 that is congruent with 1 modulo the first number and with 0 modulo both of the other numbers. Sorry, it's still p1. and you find P2 such that it's congruent with 0, modulo 7, with 1, modulo 9, and with 0, modulo 5, and do the same thing for P3. That will be congruent with 0 modulo 7, with 0 modulo 5, and with 1 modulo. I will probably write it down. A P3 such that is congruent with 0 modulo 7, with 0 modulo 9, and with 1 modulo 5. Because there's a peculiar property of remainders that if you take P1 and multiply it by 5, then take the residue after whole division with 7, you get 5, which is 5 times 1. And also, when you multiply 5 and P1 once again, and take the residue modulo 9, you get 0. And the same thing with 5. You also get 0. Well, that would mean that if we took P1 and multiplied it by 5, then edit P2 multiplied by 4, and then edit P3 multiplied by 2, we would get some number that would be 5 modulo 7 and 4 modulo 9 and 2 modulo 5. Well, that is true because P1 is equal to, is congruent with 0 modulo 9. P3 is congruent with 0 modulo 9. And P2 is congruent with 1 modulo 9. So on the left side here, you can write also 0 times 5 plus 1 times 4 plus 0 times 2, which will be 4, congruent with 4. This is a basic property of computation modulo a certain number. Actually, in general, if you take x that is congruent with y modulo some m, and you take some x prime that is congruent with some y prime modulo the same m, then that implies that x plus xy, x plus x prime is congruent with 0, I'm really sleepy now, with y plus y prime modulo m. Okay. Well, so as I said before, if we take 5 times P1 plus 4 times P2 plus 2 times P3, we find some number that has all the properties we seek. So let's try and find those P3s, P2s and P1s such that all of those apply and we will use that to compute x. Okay, so I'll start with computing the P1. Okay, so we know that P1 is congruent with 0 modulo 9 and is congruent with 0 modulo 5. That means that P1 is a multiple of 5 and a multiple of 9. And because 5 and 9 are relatively coprime, that means that if 5 is a divisor of P1 and 9 is a divisor of P1, then also 45 is a divisor of P1. 45 equals 5 times 9. So for P1 is equal to 45k. And also from the first congruence, P1 is equal to 7 times some other constant L plus 1. That is just the first congruence. P1 is congruent with 1 modulo 7 rewritten into an equation. Okay, so let's put those two equations together and see what will happen. 45k is equal to 7L plus 1. Or also 45k is equal to 45k minus 7L is equal to 1. If you already studied some algebra, this could be familiar to you. It's a special instance of the so-called Bézout identity. The Bézout identity is an equation. It says that for any two whole numbers a and b, there exist some numbers x and y, or I'll probably use some other name, a times u plus b times v is equal to the greatest common divisor of a and b. Okay. Well, so the Bézout identity could be seen as something that takes a and b as inputs and somehow gives you the u and the v, such that the greatest common divisor of a and b is equal to a times u plus b times v. The usual way of computing those is using the extended Euclidean algorithm. I should show you why this looks similar to this. Actually, 45 is coprime with 7. So the GCD of 45 and 7 is equal to 1. So if we rewrite this a bit, you could say that 45 times u plus 7 times v is equal to 1, which is the greatest common divisor of 45 and 7. So we know that P1 should be 45 times the k, or also, as I renamed it, the u. Okay, I hope you already know the Euclidean algorithm. If you don't, I guess it might be apparent how it works after I show it. It's an algorithm that is usually used to find the greatest common divisor of two numbers, but it can be also extended to give you the u and the v inside Bezout's identity, and the u and v are, by the way, called the Bezout coefficients. Okay, so let's run the extended Euclidean algorithm on the number 45 and the number 7. So the extended Euclidean algorithm works, the Euclidean algorithm works like this. It takes the bigger number and it takes away the smaller number. So the first step of the Euclidean algorithm would be this one. 45 minus 7 is equal to 38, and then 31 is equal to 38 minus 7. 31 minus 7 is equal to 24. 24 minus 7 is equal to 17. 17 minus 7 is equal to... Actually, this is a bit tedious. You can replace the step of taking away the smaller number by taking the remainder of the bigger number after dividing by the smaller number. Well, 38 is equal to 5 times 7 plus 3. So I could take away the 7 5 times and get 3. Then I would take 3 away from 7, get 4, and keep the 3. Take away 3 from 4 and get 1. Then take away 1 from 3 until I got to 0. And when I get to 0, then the other number that remains is the greatest common divisor of 45 and 7. Okay, so how could we extend the Euclidean algorithm to also give us the Bezout coefficients? We can write it like this. 45 is equal to 45 times 1 plus 7 times 0. And 7 is equal to 45 times 0 plus 7 times 1. Now, the first step of the Euclidean algorithm would tell us to take the remainder of dividing 45 by 7, which would be, let me compute for a second, that would be something like 3, because 45 is equal to 6 times 7 plus 3. So the number 3 is the next one we are interested in. And you can write 43 as is seen from this equation, like 45 times minus 1 plus 7 times 6. Then the next step in the Euclidean algorithm would be to take the remainder after dividing 7 by 3, which is 1. And 1 is equal to 7 minus 2 times 3, which is equal to, after we put inside those equations, 45 times 0 plus 7 times 1, that is 7, minus 45 times minus 1 plus 7 times 6. Okay, let's expand that. That is 45 times 0 plus 45, that is 45 times 1 plus 7 times 1 minus 7 times 6 minus 7 times 5. I'm sorry, I must have made some silly mistake. This doesn't compute. Okay, 7 times 6 is equal to 42. Aha, I got it. I switched the signs over here because 3 is equal to 45 minus 6 times 7. How silly of me. 45 times 1 minus 6 times 7, which is simply 7 times 6, and then 1 can be written as 7 minus 2 times 3, which is equal to 7 minus 2 times 45 minus 2 times 7 times 6, which is equal to 45 times minus 2 plus 7 times 1 plus 2 times 7. 2 times 6. Okay, I'm gonna make sure I didn't make some silly mistake. 45 times minus 2 is minus 90. Those parentheses add up to 13, and 13 times 7 is 70 plus 9 plus 21, which is equal to 91. So this is equal to minus 90 plus 91, which is 1. Okay, but this was exactly the point of learning the Euclidean algorithm, to get those numbers, to get this minus 2 and this 13. Remember, we tried to find some u and some v such that 45 times u plus 7 times v is equal to 1. So now we know that u is equal to minus 2 and v is equal to 13. Great. I'm going to make some space. Feel free to pause the video and catch up on the Euclidean algorithm if you didn't quite catch that. It's important to understand. Okay, so now we somehow know that 45 times minus 2 plus 7 times 13 is equal to 1. Okay, so P1 is equal to 7 times L plus 1. Where did we get that from? We got that from the definition of P1. And we see that the L is 13. So P1 is equal to 7 times 13 plus 1, which is equal to 92. Well, let's check that P1 has all the properties we wanted it to have. It should be congruent with 0 modulo 9. Well, it doesn't have the properties. I'm sorry, I must have done another silly mistake somewhere. Okay. Aha, I see. P1 is equal to I did a sign error because actually from this equation you can see that this is K and 13 isn't L, it's minus L, because we wanted it we wanted a minus sign before L. Okay, so P1 is equal to K times 5 times 9 is equal to K times 45 is equal to minus 2 times 45 is equal to minus 90. Well, that's quite strange to get a negative number in P1. Well, we can correct it pretty easily, because you see, I'm not going to prove it, but you can prove that the x will be a member of the closed interval between 0 and 7 times 9 times 5, which is equal to the interval between 0 and 7 times 45. 7 times 45 is equal to 90 times 3 plus 45 is equal to 270 plus 45 is equal to 315. Okay, so x is between 0 and 315, not inclusive. Sorry, my error. So the maximum possible value for x would be 314. Okay, so P1 is equal to minus 90. Well, we are actually computing everything modulo 315. I'm going to do it as a bit of a magic trick here. I'm going to add 315 to P1 and I'm going to say it still works. I actually could prove it, but I think it would be a bit beyond the scope of this video. Okay, P1 is equal to 315 minus 90 is equal to 225. So now I'm going to check that I finally got the P1 I wanted. I wanted P1 to be 0 modulo 9, 0 modulo 5 and 1 modulo 7. Okay, so 225, as you can see, is congruent with 0 modulo 5. That should be apparent. 225 is equal to 5 times 45. Now 225 should also be congruent with 9. Let's try some division. 225 divided by 9. Okay, that wasn't too hard. So 225 is also congruent with 0 modulo 9. Cool. And we also want it to be congruent with 1 modulo 7. So 225 divided by 7 is equal to 3 2, and the remainder is 1. Finally, we got the P1 we wanted so much. I'm going to delete some things around here, make some space, and I'm going to compute the rest of the P's, that is P2 and P3. Okay, I'm going to write somewhere around here that we compute P1 to be equal to 225. Okay, so P2 is equal to some k times 35, that is 5 times 7, and it is also equal to L times 9 plus 1. L is some integer or some whole number, and that's just a rewriting of the second congruence. So k times 35 minus L times 9 is equal to 1. Once again, 35 and 9 are coprime. Okay, let's run the extended Euclidean algorithm. 35 is equal to 35 times 1. 9 is equal to 9 times 1. Now, 30 times modulo 9 is equal to 8. Let me show you why. That is because 9 times 3 is equal to 27. Yes, 27. And 27 plus 8 is equal to 35. So 8 is equal to 35 minus 3 times 7. Sorry, I'm a bit sloppy today. 3 times 9. And now 9 minus 8 is equal to 1. 9 times 1 minus 35 minus 3 times 9, which is equal to 30 minus 35 plus 4 times 9. Great. So minus 1 times 35 minus 4 times 9 is equal to 1. Okay, so P2 is congruent with minus 1 times 35 modulo the magic number 315, which happens to be 7 times 9 times 5. So we will compute the P2 between 0 and 315 as 315 minus 35. That should be somewhere around 280 if I'm lucky on my first attempt. So let's check that it fits all the conditions we wanted it to fit. So P2 is equal to 280. Well, 280 is 40 times 7. And 280 is also equal to 5 times 48. Now, P2 divided by 9 is equal to 280 divided by 9 is equal to 3, 10, 1, and the remainder is 1. So 280 is equal to 31 times 9 plus 1. Great. All the conditions fit. So we successfully computed P2 to be equal to 280. Hooray! I'm gonna write it down under P1. And finally, there's the matter of P3. P3 is equal to some multiple of 63, which is 7 times 9, and it is also some multiple of 5 plus 1. Okay, let's do the usual rearrangement of this formula. 63 times k minus 5 times l is equal to 1. So let's run the extended Euclidean algorithm. 63 minus 5, 63 modulo 5 is equal to 3. That is 63 minus 12 times 5. Now, 5 minus 3 is equal to 2. I'm going to rearrange this a bit. Oh, I made a silly mistake. This should be actually 12 times 5. So that would be 13 times 5 minus 63. I'm going to double check that this fits. 13 times 5 is equal to 65 minus 63 is equal to 2. Great. Now 1 is equal to 3 minus 2 is equal to 63 minus 12 times 5 minus 13 times 5 minus 63. Let's expand. So 63 minus and minus gives plus. So 2 times 63 minus 12 times 5 minus 13 times 5 is equal to minus 25 times 5. And now let's check that it fits, because my brain usually has some malfunction, as Salman Khan sometimes puts it. 25 times 5 is equal to 125. And 2 times 63 is equal to 126. Hooray! So that would be 1. Good. Now we know that 1 is equal to 2 times 63 minus 25 times 5. So the k is the 2, because 2 times 63 minus, I'm going to show it around here. 2 times 63 minus 25 times 5 is equal to 1. So P3, which is equal to 63 times k, is equal to 126. Now we might want to double check that we did all our calculations okay, and I'm going to once again check that P3 is congruent with 0 modulo 7, with 0 modulo 9, and with 1 modulo 5. Well, the last one is pretty easy to see, because 126 is equal to 125 plus 1. This is obviously divisible by 5. 126 divided by 9 is equal to 1, plus 36 divided by 9 is equal to 4, and the remainder will be 0, and 126 divided by 7 is equal to 1, remaining 5, so 56. 56 is equal to 8 times 7, and the remainder is 0. Great. So we checked that P3 fits. So we computed all our P's, and it seems that we didn't make any silly mistakes, finally. And now I'm going to do the magic of multiplying p1 by 5, p2 by 4, p3 by 2, and get the x we wanted. p1, as you recall, is congruent with 1 modulo 7, with 0 modulo 9, and with 0 modulo 5. So if I multiply p1 by 5, I will get some number that is congruent with 5 modulo 7, with 0 modulo 9, and with 0 modulo 5. And if I add to it the correct multiple of p2 and of p3, I will get some number that correctly fits all the conditions for x. So p2 times 4 plus p3 times 2. The 5, 4, and 2 are the remainders given by the conditions for x. So let's do the grand calculation. 225 times 5 plus 280 times 4 plus 126 times 2, that is equal to 5, 2, 2, 1, 1. You know what? I'll just do the calculation somewhere else because I'm prone to failing if I do it in my head or on paper. So how was that? It was 225 times 5 plus 280 times 4 plus 126 times 2. Okay, 2497. So this number should fit all the conditions we put on x. So let's try to get the remainder of the remainder after dividing 2497 by 7. 2497 divided by 7 is equal to, there's 3, 19, 2, 57. Now 7 times 8 is equal to 56. I see. I once again had a brain malfunction because there should be a 3 here, because 3 times 7 is 21. 39. Well, there would be a 5 and a 47 would remain, and 42 is equal to 6 times 7, so 5 will be the remainder. Great. The first condition seems to fit. Now let's check the second condition. You know what, I'm going to just remove all this stuff about P1, P2 and P3. I hope I was clear enough for you to understand what those numbers mean. If not, feel free to watch the video again or tell me what a bad teacher I am. 2497 divided by 9 is equal to 2, remainder 6, 9, there's 63, remainder will be 6, 7, 67, 7 times 9 is equal to 63, so the remainder will be 4. Great! The second condition is also satisfied. Now 2497 divided by 5 is equal to 4, remainder 4, 49, 9, 47, 9, and the remainder will be 2. Good. So right now I proved that 2497 is a solution to this system of congruences. But as I promised to you, there is also a solution between 0 and 315. And that solution is congruent with 2497 modulo 315. Or also you could say that the solution is 2497 modulo 315. Okay. Well, I'm going to do the division. 2497 divided by 315 would be, let me take a guess, something about 7. Okay, 7 times 5 is equal to 35. 3 plus 7 is equal to 10. 1 plus 21 is equal to 22, and the remainder is 292. This number is less than 315. And let's try and check that it also fits all the conditions. So 292, let's divide it by 7. So that would be 4, the remainder is 12. 12 divided by 7 is 1, and the remainder is 5. Great, first condition is satisfied. Now the second condition, 292 divided by 9 is equal to, okay, that would be 3, the remainder is 25, okay, that would be 2, and the remainder is 4. Great. Second condition, check. And now we're in the final stretch. 292 divided by 5. Well, it's no rocket science. It's equal to I made me some problems. Actually, the remainder of 292 after division by 5 is 2. It should be obvious because 290 is a multiple of 5. Okay, all conditions fit. So the smallest natural number that fits all of those 3 conditions is x is equal to 292. Well, okay. I hope you enjoyed watching me stumble through solving this system of congruences, and I will make just a very short review of what we did. We found some P1, P2 and P3 such that P1 is congruent with 1, modulo 7 is congruent with 0, modulo 9, and with 0, modulo 5. P2 such that it's congruent with 0, modulo 7, with 1, modulo 9, and with 0, modulo 5. And a P3 that is congruent with 0, modulo 7, with 0, modulo 9, and with 1, modulo 5. To find those, we used the extended Euclidean algorithm, and after we got them, we just took P1 times 5 plus P2 times 4 plus P3 times 2, and we got some particular solution. And to get the smallest natural number that is also a solution, we just took the remainder after dividing by 7 times 9 times 5, which is 315. Okay, I hope you enjoyed watching this video, and see you guys later.